Hello everyone, welcome to the video tutorial on Firebird V robotics research platform. This platform is based on the ATmega2560 microcontroller. In this tutorial, we will learn about stepper motors, ways to control them, and how to interface a stepper motor with the Firebird V robot. Let's see the agenda for discussion in this tutorial. First, we will have an introduction where we will discuss what is a stepper motor and its types. Then we will move on to learning how to control a stepper motor in different stepping sequences like wave, full, and half stepping modes, followed by a comparison of three stepping modes. Then we will have a short demonstration of how to identify the wires of a usually unlabeled stepper motor. This will be followed by a discussion of the circuitry required to drive a stepper motor, and then we will finally jump on to actually programming the robot to control the stepper motor. Prerequisite knowledge. Before we jump on to learning how to interface stepper motors, make sure you understand input-output interfacing using ports in AVR and know the time of features in AVR and how to use them. So the first question that arises is, what is a stepper motor? A stepper motor is a special kind of motor whose rotation is divided into discrete steps which allow precise control over its angle. It can be commanded to hold a step or move to the next step. Types. Steppers are mainly classified on the basis of the internal wiring. These classes are as follows. Bipolar stepper motors usually have 4 wires to control them and the drivers are complex. Unipolars, on the other hand, have 5 or 6 wires and are relatively easier to drive. Since unipolars are more commonly used, we will be using them in this tutorial. Moving on to how to control a stepper motor. A stepper motor can be controlled by sending specific sequences of signals to its wires. The different stepping sequences are wave stepping, full stepping, and half stepping. We will now see and understand how to use each one of them. Wave stepping. It involves exciting each coil turn by turn in a circular fashion. The table shows which coils are to be excited for generating the wave stepping sequence. Here, a 1 denotes on, whereas 0 denotes off. To rotate the stepper motor in one direction, we send the sequence 1, 2, 3, 4, 1, and so on, while for the opposite direction, we send the sequence in reverse, that is 4, 3, 2, 1, 4, and so on. Shown here is an illustration that depicts the direction of the rotor inside a stepper motor in the wave stepping sequence. The rotor points to the excited coil at that instant. When coil A is excited, the rotor aligns itself to point to it. Next, when coil B is excited, the rotor turns to align itself again. This process repeats for the other coils. Full stepping. It involves exciting two adjacent coils turn by turn in a circular fashion. The table shows which coils are to be excited for generating the full stepping sequence. Notice that at each step, exactly 2 coils are excited. Now let's see what happens inside the motor when 2 coils are excited at once. As you can see, when 2 coils, say A and B, are excited, the rotor settles between them. This results in a higher torque than that found in wave stepping. Half stepping. This stepping mode is a combination of wave and full stepping. Now, if you look closely, half stepping uses full stepping between the step positions of wave stepping. Let's see what happens inside the motor during the sequence. As you can see, there are 8 positions corresponding to the 8 steps shown in the previous table. It is called half stepping because it effectively halves the step angle and offers more resolution. We will now see the differences and similarities between the 3 stepping modes. Talking about torque, since only one coil at a time is energized in wave stepping, its torque is the lowest. In full stepping, 2 coils are excited at once, creating a larger attractive force, resulting in a larger torque. Since half stepping excites 1 or 2 coils per step, the torque output is intermediate. Vibration in a stepper motor increases with torque and decreases with the step angle decreases. Since wave stepping has a low torque but a step angle larger than half stepping, it has an intermediate level of vibration. Full stepping, on the other hand, has higher torque resulting in more vibration, and half stepping, due to small step angle, exhibits the least vibration. Next is speed. Speed is equal to the step angle times the step frequency. Since the step angle is the same for wave and full stepping, they have the same speed. For half stepping, the stepping angle is halved and thus the speed is also halved. Resolution is fineness of control over a rotational angle and is equal to the step angle. The step angle is equal for wave and full stepping while it is halved for half stepping. We will now learn how to identify the wires of a stepper motor.
Most of the stepper motors do not come with the wires labeled or some data sheet specifying it. So to figure out which wire is which, let me show you a simple way to do it using a multimeter. Take the stepper motor and strip its ends if it is not already. This one is a 6-wire unipolar stepper motor and has 2 common wires. To identify them, connect one wire to one leg of the multimeter and serially try to check the resistances with each one of them. The second wire shows a resistance of 7.5 ohms. The third wire shows an open connection. The fourth wire again shows 7.3 ohms. Thus we have identified a coil whose center tap is the first wire, that is the green one, and it ends being the second and the fourth. Repeating the process for the open wires, let's connect one lead to the third wire, that is the orange one, and the other to the fifth one. This shows a resistance of 13.5 ohms, which seems to tell me that I have the opposite ends of the coil, and the last one, that is this one, is the common wire, that is the center tap wire. Seeing the resistance with the last wire indeed shows me 7.3 ohms. By this we have identified that the green and the black wires are common wires. We will short them together and treat them as one. Note that the order of the 4 wires cannot be determined by this method. This can be only found by actually running the stepper motor with random assignments of connections and swapping the last two if it just wobbles instead of rotating.
This is a circuit diagram for the stepper motor driver. The ULN2003 is a transistor array package of 7 transistors that are capable of switching 500 milliamperes of current per transistor. The pins 1 to 7 are the inputs to the transistors, while the pins 16 to 10 are the corresponding open collector outputs. All transistors have a common emitter that is connected to the ground at pin 8. The COM pin at pin 7 is connected externally to the supply voltage. The circuit is basically used to drive the stepper's high current windings by a microcontroller's general purpose I/O pins. We will now discuss how to interface the Firebird V robot with the stepper motor using this circuit. These are the Firebird V robot's expansion slot pins, which we are going to use to connect to the driver circuit shown previously. Expansion slot pin number 17, that is PL7, is connected to the ULN2003 driver IC's pin number 1. The expansion slot pin number 18, that is PL6, is connected to the driver IC's pin number 2. The expansion slot pin number 19, that is PD1, is connected to the driver IC's pin number 3. The expansion slot pin number 20, that is PD0, is connected to the driver IC's pin number 4. Expansion slot pin number 23, that is ground, is connected to the driver IC's ground on pin number 8. The pins are numbered on the slot as shown in the figure. Note the unusual snake-like numbering of the expansion slot. Pins 5 to 16 and 25 to 52 are not shown for clarity. We will be using the pins 17, 18, 19, 20 and 23. Now for an example, we will be rotating the stepper motor in one direction at a fixed speed for a complete revolution and then change its direction and repeat the process in the opposite direction. For this, we can either use delays between steps or we can use one of the AVR timers for the delays. For a challenge, let's talk about achieving this with the second method. So moving the stepper a single step every 3.33 milliseconds means running the motor at a step frequency of 300 Hz. To achieve this, we select the 16-bit timer 1 and run it in CTC mode, that is, clear on timer compare match, by setting the waveform generation mode bits, that is the WGM mode bits, to 0100. We will set the prescaler to 1 as we do not need the timer clock to be divided by any factor. Since the required frequency is 300 Hz, we set the top value to 49,151 as calculated by the formula. The timer's OCR1A register value is used as a top value in CTC mode. Finally, we enable the compare match interrupt to step the motor in the interrupt service routine every time a compare match occurs. Now that we have understood how to use the timer for our purpose, let's have a look at the code. This is a list of headers to be included, which are avr/io.h, avr/interrupt.h, and a custom header called stepper.h that contains the functions for controlling the GPIO pins of the stepper in different step modes. The interrupt service routine is called whenever a compare match occurs, and we will use it to make a single step. Direction here is a global variable that is initially set to +1 and is changed to -1 after every 200 steps by the following code, which increments step count in each call of the ISR and changes direction from +1 to -1 and vice versa if the step count exceeds 200. It then resets the step count to 0. The stepper motor we use completes a revolution in 200 steps. Modify this value in if condition if the stepper motor's steps per revolution value is different. Moving on to the main function, first we initialize the I/O ports for the stepper motor. Then we set up timer 1 with the configuration we decided upon. To do this, we first temporarily disable all interrupts by setting up and set timer 1 to work in CTC mode by setting WGM bits to 0100 in the TCCR1B register. Only WGM12 is set as the other WGM bits are by default 0. Then the output compare match interrupt for timer 1 is enabled by setting bit OTIE1A in the TIMSK1 register. Finally, we re-enable all the interrupts after initialization. We then set the top value in the OCR1A register using the given formula. Here, f_CPU and speed are previously defined constants whose values are 1474560, that is 14.7456 MHz, and 300 respectively. Then we finally start the timer by setting the prescaler to 1 through the CS12, CS11, and CS10 bits in the TCCR1B register. Then we hand over the job to the interrupts and let the processor go into an infinite loop. Now let us try to program the robot in Atmos Studio 6. Follow the usual steps of creating a new project and selecting the microcontroller as ATmega2560. Here, I already have the project set up. As you can see, the first line of our code has the f_CPU declared as 14745600, which is the clock frequency of the microcontroller on Firebird V. The next line defines speed as 300, which is used to indicate the stepping frequency of the stepper motor. The next few lines are the include directives for the usual I/O and interrupt libraries and for the stepper.h custom header file, which we will discuss in a short time. After this, these two lines declare the global variable step count and direction that hold the count of steps rotated and the direction of rotation respectively. +1 here denotes clockwise direction and -1 denotes counterclockwise. Whenever you use global variables inside interrupt service routines, you should always declare them as volatile to prevent compiler optimizations. Not using volatile may or may not make the program work, so it is always a good practice to have it when using globals in interrupt service routines. Next is the interrupt service routine for the compare match interrupt. This has already been explained earlier in this tutorial. The last function in this file is the main function, which also has been explained. Now let us move on to the stepper.h header file that contains the stepper control functions. The first two lines are used to avoid users of this header file from accidentally including the file twice. Don't worry if you don't understand how it works. Moving on to the subsequent lines, these four lines are used to specify at which ports the four stepper wires are connected to. Moving on to the subsequent lines, these four lines are used to specify at which ports the four stepper wires are connected to. The next four lines specify the pin numbers of the ports at which the stepper wires are connected. Next is the stepper port initialization function that sets the data direction bits for pins PL6, PL7, PD1 and PD0 as output. Next is the wave step function that takes in the direction argument and takes a step in that direction. The first line declares a static variable step index that stores the number corresponding to which step of the sequence the stepper is currently in. The next line either increments or decrements the step index based on whether direction is +1 or -1. The expression adds 4 and a modulo 4 is performed to continue from 0 if step index goes to 4. The effect is that step index is always 0, 1, 2 or 3. Then depending on the value of step index, we send the corresponding step sequence. Here, coil A port is odd with 1 shifted by coil A pin. This has the effect of setting coil A pin to 1. Similarly, the next three lines set the other pins to 0. This technique of using bit shifts and ORing and ANDing is called bit masking. The other case statements in the switch block and the corresponding bit patterns is discussed in the wave stepping section previously. Similarly, the next function full_step achieves a similar purpose, but for the full stepping sequence. The only difference here is in the bit pattern being sent. The next function is half_step, which also works similarly, except that it has 8 steps and so its expression adds and divides by 8 instead of 4. The switch block here has 8 cases, that is, from 0 to 7 for each of the bit patterns of the half stepping sequence. Now let's build the code and burn it on the robot. We will now see the stepper in action in the following clip. So by now, we have successfully understood the control of stepper motors and how to interface a stepper motor with the ATmega2560 based Firebird V robotics platform. You may modify the code to experiment with different stepping modes and speeds, or by setting it to specific angles, etc. With this, we have reached the end of this video tutorial. Thank you for listening. For any doubts or suggestions, feel free to mail them at helpdesk@e-yantra.org. This is Joel Pinto signing off.